Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, so thank you for inviting me, and I'm really looking forward to this. I've had a great time so far. So I'll talk about distributed file systems, and just to give you a little bit of background and motivation and just context for what I'll be talking about. I faced a problem coming here, and that was I wanted to share my travel itinerary, and I had a bunch of devices. I've got my laptop and a tablet and a phone, and it's useful to have my travel information on all of those. My assistant was arranging things, and so she's got her computer, and then my wife also wants to know where I'm going, and so she's got a machine and a tablet and a phone as well. And one thing I could do, and a common thing a few years ago would be every time anything changed in my itinerary, I could email that out to everyone, and they could get the email, and then they could store it locally. And then if it got updated, I could email it out again, and they could maintain those updates. And they would sort of be running this distributed file system, all of us in our heads. That's a really silly thing to be doing at some level. And so what I'd much rather do, and in fact what I did do, was I stored this all on Dropbox, had a shared folder. We all have local copies of it and can access this data locally. And when I update things, or if my assistant updates things, it just, everyone can see those updates, right? Much more convenient. Talking about distributed file systems is a little bit, funny at some level, because when I was, a student, it was just natural. That's the way files were done, right? So I had a workstation, and you would never think of storing data on a workstation. But we've then gone through this evolution where, kind of this PC era, where everyone walks around with laptops or desktop PCs, where most of the data is stored locally. But what's happening is we're moving to this world, kind of back to the future of where distributed file systems are going to be the way we store data. And it's partly being driven by this diversity of devices. Right? Back when I only had one laptop I needed to take care of, maybe this was manageable to do manually. But as I have more and more devices, it's just not fun to have to do all this stuff manually. But there's also another aspect to distributed file systems that's driving this. If you look inside of Dropbox, they also are running a big distributed file system, right? So all my stuff doesn't fit on one server there. They've got thousands, hundreds of thousands of clients, and so they have racks and racks of machines, and they need to distribute the data across those machines. Right? And this is another reason that end users are going to be moving more and more towards using distributed file systems. Not only is it more convenient because of these devices, but also having a dedicated professionals maintaining your data makes a lot more sense than trying to do it yourself. Right, so they can, at Dropbox, they're much better at backing things up. They can do geographic replication and so on. And so over today and on Friday, I'll be talking about some aspects of distributed file systems. And you can really think of this, the topics that I'm going to try to cover in two kind of orthogonal directions. First, I'll be talking about some fundamental challenges that you'll see over and over again. These are challenges like getting good performance, dealing with faults, having good availability, reliability, right? But also having consistency, making sure you actually get the right answer out of the system, and keeping the system simple enough to implement, reason about, and get right. To talk about these topics, I want to talk about them not just in the abstract, but talk about them in the context of specific systems. And so we'll go through a series of systems, and this will really be how the organization is driven. And we'll talk about some simple client-server systems, or just sort of very briefly, if you just kind of did the first thing that came into your mind to build a file system, what would you get? And so we'll talk about some very simple things like NFS version 2, the HTTP protocol does similar things, just very basic ideas. That'll have some problems, and so we'll look into more consistent client-server systems that get more things right. Systems like AFS, NFS v4 has more of these features in it. Coda, talk probably a little bit about Bayou. And these will be systems that I think do a better job of getting the right answer, and so they'll show you some of the principles that I think are important. in addition to these consistent file systems, there are cases where you have to relax consistency to deal with mobility. Right? So in this context, I've got my laptop and tablet, and we're not always connected to the network, and so what do we do in those cases? Coda, historically, and Dropbox today have to deal with these issues. So we'll talk about what you do in those cases. And then finally, we'll talk about cluster file systems. And depending on the amount of time, I should be able to talk about things like the Google file system, HDFS, and maybe also talk about what lays on top of those, things like Bigtable, HBase, and Azure. So that's kind of the agenda for the next today and on Friday. The way I'm going to do this is there's roughly 4 parts to this discussion. The first part will probably be a little shorter. You can think of them as an hour each, but I expect this first part to be a bit shorter than that. This will be around that. We'll see how time goes after that. And so as a starting point to kind of make sure we're all on the same page, I just want to begin by talking about some very simple distributed file systems. And so I'll talk about just an RPC-based file system and NFS version 2 will be my case studies to talk about there. And looking in the other direction, the challenges and principles, kind of what's happening in this space is simplicity on one hand versus performance and consistency and fault tolerance. Okay. And so we'll start with that. And the conclusion, just to let you know what's happening, is that they don't do a great job in giving you the right answer, and so we need to talk about what is the right answer. And this will touch on some topics that we've already talked about over the last few days. But so we'll see how fast or slow I should go through that. But the question will be, what is the right answer in these systems? And then having defined the right answer, we can talk about how to get the right answer in a distributed file system in several different contexts. And so we'll talk about the AFS file system for relatively strong consistency when you have good network connections, and Coda as an example of a mobile file system when you don't want to count on having network connections all the time. And in the context of these systems, there's this fundamental set of trade-offs of consistency versus availability versus fault tolerance that these systems play in different ways. And then finally, the last topic we'll talk about will be cluster file systems. As I said, I expect to cover the first 2 topics today. We may begin a discussion of some of these systems today, depending on how the time goes, but most of this will be covered on Friday. Okay? All right, so starting off with these very simple distributed file systems. And this will be fairly quick. Ask questions, absolutely, if it's too quick. But I think some of these ideas are probably have seen before. Okay, so the first thing you might try to do if you're building a distributed file system is to take advantage of remote procedure call. Remote procedure call, so you've got this local file system, right? And so we know how to build a local file system, I'll assume. Here's my file system. I have applications that access it. This is in the kernel. I use system calls to access my local file system. It manages the disk, and I've got some interface that lets me open and close files, read and write them, and so on. And so one thing that I might do is take advantage of RPC. Right? That RPC, remote procedure call, is just a push button recipe for taking local procedure calls and making them into remote procedure calls. And so in fact, I can mechanically have a compiler generate for me stubs at both the client and the server and pass information across the network where I would have, in the past, would have put it on the stack and jumped to a different program counter. Right? So this is very simple. It's automatic. You can just feed this stuff into a compiler. Your local file system is now a distributed file system. So thank you very much, and we'll go on to the next topic. So it is simple. It supports sharing, but it has some problems. And it sort of has the obvious problems of performance, that your local memory is a lot closer than someone's remote memory. It has problems of scalability, that if every procedure call goes up to a server, the server's handling a lot of requests per second, and it has the problem of availability. Right? If the server dies, everyone in the department goes and gets coffee. Right? You're stuck for the day. And so, anecdotally, and I don't have a source for this, but what I've heard is that people using Novell NetWare, this was one of the first systems that did this, the mode of operation was you got into work in the morning, you copied the files off of the distributed file system to your local file system, did your work locally, and then at the end of the day, you hopefully remember to copy it back to the server so it would get backed up overnight. Right? So, not quite the solution we were looking for. And so in the mid to late 80s, Sun came up with the network file system, and the one that was released and became very widely used was NFS version 2. And I should emphasize this has been supplanted by version 4 at this point, although you'll still see version 2 out there being used. And a big part of what they were looking at was how to get acceptable performance. Right? Can we make this distributed file system running at the time on probably a 10 megabit per second Ethernet, can we make this have acceptable performance? And so the important architectural change that they made was to add a cache at the client. And this was in the client's memory. And so the hope was that most of your requests could be serviced by the client's local cache, and you would have to go to the server only occasionally. And so this kind of works in the obvious way. If you read data, you can then put it in your cache. After you've done that, I guess we're going to put it in the other cache as well. After you've done that, you can read it locally, and that should be a very fast operation. In order to make writes have good performance, instead of using a write-through policy, where every write goes to the server, writes, again, are just going to go to local cache memory. But, of course, that's not going to completely solve the problem. That'll make writes fast, but ultimately you need to get the data to the server. And so after doing several writes, when you close the file, the writes are pushed back to the server stores the data on disk, and then acknowledges that it in fact has the data, and at that point you're done. Okay? But there's a problem, right? They've got this other client still happily reading the old version of the data. It's very fast, but it's not seeing the new data. Right? And so NFS faced a number of challenges, and the first of them was consistency. Right? That this cache data may not reflect recent updates. And so the solution, to use the term a little bit generously, was weak consistency. And the way this worked was a client could read from its cache for a certain period of time, but if it's been more than, this was a configurable amount, but if it's been more than 30 seconds typically since the client is checked with the server, then when it tries to read from its local cache, it's going to go to the server. It does what's called a get attribute request. It basically asks, when was the last time this file was modified? If the file has not been modified since the cache version, then we can just go ahead and use the cache version. Right? And continue to use the cache version. But eventually, if some other client writes the data, I'm still, of course, reading the old version even though it's been updated. They'll close the file, send it back to the server, and I'll still read the old version because it hasn't, my time hasn't gone, but eventually I'll do the get attribute request, find out that the file has changed, and at that point read the new version, update the new version in my cache. Right? So here we've learned an important lesson, and so you've probably heard of the first law of computer science, that any problem can be solved with an additional level of indirection. Right? But what we learned from NFS is Deline's law of computer engineering, which is I can make it go as fast as you want as long as you don't mind getting the wrong answer. So, all right, so that's their solution to cache consistency. Get it more or less right, and and sort of hope things will work. And it generally does work, because if you looked at typical workloads of the time, files were typically widely shared, but read-only, or used by one user and read-write. There were very few files that are widely used and read-write. And so in this world, this is probably a reasonable trade-off to make, but it gives you unfortunate consequences. I remember when I was in graduate school, we were working on the network of workstations projects, and one of my colleagues built a system for parallel make. The idea was that you typed gmake, it was the Glunix system, you typed gmake, it spawned a bunch of processes across your workstations they all did a make, right? Made different part, or they all did makes on different parts of the file, and most of the time, then you ended up with a newly compiled file. But occasionally, what would happen is you changed the source file, type gmake, everything recompiled, you got your new binary, you executed the binary, and you're running your debugger and saying, wow, that should have fixed this problem. And only to realize after scratching your head for a while that, in fact, you were still running the old version of the code because the new compilation didn't see the updated file, right? Which is just intolerable. And so that small bit of inconsistency, in fact, was enough to basically make the parallel make useless. We were all much happier waiting a minute for a big make to finish, knowing that then I could trust the program, than to just get then to get an answer back in 10 seconds and try to debug this thing that maybe changed, maybe didn't. All right, so we'll come back to this problem later. The second challenge that NFS faces is fault tolerance. So we've heard about this already a lot, that when I go from a centralized system to a distributed system, a lot of new failure modes arise. If everything's centralized, you have fate sharing. Either everything's dead or everything's alive. Right? But in a distributed system, a lot of things can happen. Right? One very simple thing that can happen is the network can fail in some way. Maybe it just drops some packets because it's overloaded, or maybe someone unplugged a wire that they shouldn't have unplugged. And so NFS, we're really focusing on simplicity here. They wanted to get a simple system. What happens if a request is lost? Just retry. And so if you send enough requests, eventually the network gets repaired, and one of your requests makes it through, you get your answer back. Okay. You can do the same thing if the server fails. You just keep sending requests. When the server comes back, you get your answer back. Okay, so that seems fine. But there are some issues with this approach. Remember that our standard file system interface, when this was being built, said you open the file, then you read and write the file, then you close the file. And there were, so I open a file, I get back a file descriptor, and then the server crashes, and I tell the server that I want to read from file descriptor 17, and it has no idea what I'm talking about because it crashed. Right? It doesn't know what file corresponds to this, to 17. So you have to change the API. Instead of saying, open the file and give it a name, and then get your file descriptor back, they make a small change. In NFS, you got what's called a file handle instead of a file descriptor by looking it up, and then you could read from the file handle. This looks very similar. The difference was that the file handle was a persistent identifier for the file. A typical implementation was that the file handle would be the inode, or the I number, plus a version number. Right? And so even if the server crashes and recovers, the file handle that you got before should still be useful for accessing this file. And there were other things that you had to do. For example, making the system, so this is we had to retry, we have to make the system stateless so that it can continue to operate. I can write a file. Typically, this is when I'm closing it, typically most file systems at the time and still would store a write in memory until you did a flush. But of course, that could really confuse a client. If you did a write, you get back an OK, and then the server crashes and your data goes away, that would be bad. And so in NFS, you had to wait. You would write to the server would send the data to the disk, it would get on disk, and then only then would it acknowledge, saying, yes, your write is complete. So you don't get surprised if then the server crashes. So we had to change the API, change things carefully to deal with this stateless problem. And then third, there's another aspect of sort of this retry strategy they had to deal with, and the solution was what's called item-potent requests. Here's the problem. Suppose I issue a write, and the write makes it to the server, but the acknowledgement doesn't come back. So as a client, I don't know if that write happened or not, and according to NFS rules, I'm going to retry, so I send another write request. So if I have a standard local file system, right? What happens if I issue 2 write requests, typically? Right.
Because the file offset would have changed after first write, so the second write would append the, would be appended.
Right, yeah, so the file offset changed on the first one, the second one then gets appended, so I've actually have done 2 writes. Right, I've written some data, and then I've advanced the file pointer and written some more data. Right, so which is not what I expected, certainly, and probably not what I wanted. And so, again, to deal with this partial failure situation, I need to change my API so that I have idempotent requests. So instead of having this file descriptor that implicitly keeps track of where I am in the file, I make that explicit in all my calls, and read calls, write calls, and so on. And so I'll write my file handler, but now I specify the offset that I'm talking about, rather than letting that be implicit based on the past history of my requests. Okay? So none of these changes are difficult, but I have to go through the entire design to make this work. And so, you know, the hope when remote procedure calls were invented was that you would take your centralized system, push a button, recompile it, the stubs get put in place, and now I've got my distributed system. But the reality, at least for NFS, was that RPCs just didn't solve the problem. That because I had performance, I had to go in and add caching, performance issues. Because I had to deal with failures, I had to go through every single method and think about, for this method, what would happen if there was a failure, if there was a retry, what could happen, and redesign the method subtly, just usually small changes to make it work in this world. So make the methods idempotent, make them stateless. This, of course, feeds back into performance because now I have blocking writes. This is one of the big performance problems of NFS v2. I have to deal with both performance and simplicity versus correctness, and the solution there was we'll just have weak consistency, get it kind of mostly right. And NFS still has this problem of limited scalability, that you're sending lots of requests to the server. Even if data is cached, clients are going to the server saying, did this file change? Did this file change? Did this file change? And that turned out to be a lot of load on the server. And so this hope of pushing a button and having everything work just didn't turn out to be true. We had to rewrite everything, weaken the semantics. A lot of hard problems, it turned out. So if we go back to this set of fundamental challenges that we started with, NFS for the performance problem went to caching. For performance and simplicity, making that balance, they decided weak consistency would have to be good enough. To deal with failures, they had to change the methods, and they didn't deal with scalability too much. So that's kind of this background, right? This is where if you start building a system and do some very simple things, this is what you end up with. This is what NFS ended up with, and I still am irritated. A decade later, once all these limitations were well understood, when HTTP came along, they basically ended up with the same design fundamentally and the same problems. So at some level, I think for me, the unforgivable sin is giving the wrong answer. I can deal with a lot of these other limitations, but giving the wrong answer is not great. And so we have to ask the question, what is the right answer? What should we be doing? And so now what I want to talk about is memory models. And I'll kind of address this in a couple of directions. The first is to try to lay out the design space for memory models. And I'll argue that we can talk about consistency, coherence, and staleness. And this is an area where we as operating systems and distributed systems people often are a little bit sloppy. But I'll take some inspiration from the architecture people that are typically more careful about this than often we are. And also, as we talk about these trade-offs, the reason that it's interesting to talk about a design space is that as much as I think correctness is the thing you look for first, there are some fundamental limitations here that prevent us from always building what you would think of as the most correct answer. Right? And so I'll talk about the cap limitations and some related limitations. So given that NFS, I hope we can all agree, gives the wrong answer, what is the right answer? And the intuition that we'll often start with is we want everything to act like kind of a local memory, a local file system. When you do an update, everyone else will see the update. We can sort of informally know what we mean. If you just look at local memory, for example, the simple model that, of course, doesn't hold for modern machines, but the simple model, the one that programmers start with, is that we have these atomic operations, load, store, maybe a test and set operation for synchronization. And even under this model, writing multi-threaded code is challenging. Right? Figuring out what could happen with all these different interleavings is very difficult. I teach undergraduates this every year, and it's a struggle for people to get their heads around this. And certainly, if you ask practicing programmers, this is something that they worry a lot about. Is can you teach? Can people learn to write multi-threaded code? So some of the more difficult code people write. In this environment, we go to a distributed system. Things just got a lot worse. Right? That reads and writes are no longer atomic. Right? I saw an NFS. I update my local cache. A while later, the centralized cache gets updated. A while later, other nodes may see the update. This happens for kind of a bunch of reasons: caching, buffering writes. Some file systems have multiple servers, and so there's no central point of synchronization. And so if it was difficult to reason about programs on a centralized machine where these operations were atomic, it seems like we're doomed in this environment where things are much less certain. And so how are we going to write and reason about distributed programs where things have just gotten harder in these ways? And so what's the right answer, right? We can agree that NFS is wrong. We could say like centralized memory, but what does that actually mean? And in fact, today, centralized memory is not like centralized memory. It's complicated in its own right. So one way that I think is useful to think about this is that there's a three-dimensional design space for talking about the memory model. And one dimension is freshness, right? That's how long from when I do an update until everyone's going to see it. Another dimension is coherence. This will have to do with the ordering of events to a single memory location, and consistency, the ordering of events to multiple locations. Okay. But these are subtle and tied together concepts. So let me define each dimension a little bit more carefully and give an example of each. So if I look at coherence, coherence is going to restrict the order of reads and writes to one location. Right? So if I look at one memory location, and only look at that one memory location, and I ask the question, is the memory system or this distributed storage system playing tricks on me? Right? And if I can tell that it's not quite right, not quite a centralized system with atomic operations, then we've weakened coherence in some way. And so here's an example of this. Very simple. I've got my two-line program. So suppose that process one is just incrementing a counter and writing each value to some shared memory location or shared storage location A, and another process is reading through, or is incrementing values and reading whatever is currently stored there. And so the question for you is, in an asynchronous system where we don't ahead of time know how fast the different processes are running or how long messages in the network may take to propagate, at what point has the system violated sort of what we would expect from a simple local memory? Okay? So suppose that so I'm showing sort of what's being printed out by process 2. So it prints out a 1. That seems okay, right? Prints out a 2. Is everyone happy with that? Seems like something that if your local memory did this, you'd be satisfied. 3. prints out another 3. Is that okay? Right, that could happen on a local machine. If this were 2 threads on a local machine, a very simple memory, you could see, it could stutter. That could happen because this one's running a little bit faster than this one. Prints out a 4. That seems sensible. Prints out a 9 next. Is that okay? Right, same sort of thing. This was going faster for a little while. A 10. So 9. All right, so I'm getting no's. Okay, right. So that shouldn't happen. Right, things went backwards, and you wouldn't expect that on a local machine. Right? So why might this happen in a distributed system? Could this happen in NFS? Anyone want to argue that it can't, or definitely could? Give an example of how it could. There are multiple servers would be an example of this, right? So in a simple NFS probably wouldn't happen, but if you had multiple servers, this could happen, where an update made it to one server, and then maybe there's a failure, you fail over to the other server, and read an old version. So yeah, that'd be a good example of that. Some other, let's see. Yeah, another example of this, kind of in the same vein, would be a cooperative caching system, right? If you could read data from peers rather than always going back to the server, well, maybe one peer has seen the update, but another peer hasn't seen the update. Okay, so the next dimension to talk about is freshness. All right, and freshness is going to restrict the maximum real-time delay from when a write completes to when reads are guaranteed to observe the write. So previously we were just talking about orders of operations in an asynchronous system. Now we're adding this notion of time, which is something that, again, you kind of expect from your systems. So there's a lot. I think this is fairly intuitive. This is a dead simple example where one process is printing updates to a stock price, let's say every second, and then on another machine we're reading the current stock price. And I think there's no prize for getting this right. So where is it stale? Well, you see sort of a couple of updates, but then you keep seeing the same version for a while, and suddenly the price changed dramatically. In this example, it's very obvious that something bad happened because I included the time in each of these events. So you as a reader would never get fooled. You would see that something is wrong in the system. But of course, it'd be a lot more subtle if all I was doing was showing you this sequence of prices, and you as a trader perhaps were happily thinking that your stock was doing fine, but instead it was falling through the floor. And unfortunately, right, in a lot of systems, it's exactly when the system is very busy and things are interesting that it might fall behind and you start getting stale answers. So, why might a system exhibit staleness? Could NFS exhibit staleness? Right, this is sort of the dimension where we can understand NFS most obviously. NFS does this polling every 30 seconds, and so even from the time, if we call write complete the close by the client, by the writer, there still is a window configurable, let's say 30 seconds, where you could see the old data. So staleness gives us an ability to talk with some precision about NFS, the way in which NFS doesn't get it right, and we could also see how if we turn the knob and reduce that time, it'll exhibit less staleness and it'll feel more correct. The final dimension is consistency, and it's closely related to coherence, but it is a slightly different property. And so what consistency does is it restricts the order of reads and writes across multiple locations. Right? Coherence just looked at one location. By looking at one location, can I tell the memory system is playing tricks on me? With consistency, I can look at multiple memory locations and ask if the system is playing tricks on me. So consistency is a stronger property. Or in other words, I as a user, if you can fool me, I can look at these many locations and it all looks fine. That's a stronger property than if I can just look at one location and see that it's fine. Okay. So to illustrate that difference, let's look again at another very simple program. process 1 is going to go and increment a value and then write it to A and then to B. And process 2 will read these values and print them out. Simple little program. And the question is, again, where does the system exhibit inconsistency? Where does it not act like what you would expect from a local memory with atomic reads and writes? All right, so prints out 0, 0. Seems okay. Prints out 0, 1. Is that okay? See some shaking, some yes, some no. So who would say this is okay? Who would say this is wrong? Who would say, who's not sure? Okay. So I think this is okay, actually. Right? And the way this can happen, even if you were just running 2 threads on a local machine, is what's going to happen. So I'm first going to read. Then the scheduler is going to run this, and I'll write, and then I'll read again. Right? So I saw the 0 for the A, but I see the 1 for the B. Right? So that could happen. But you know, remember, the sort of point of all of this is these things are subtle. And they're subtle even if you have strong guarantees. Right? And so we have to be very careful if we start weakening things. All right, so then we see, next we see 1, 2. Same, you know. So now so what happened? We came around again, we read the 1 that we just wrote, and then make this into a 2 and a 2, and we read the 2. So that seems fine. 4, 3. Okay, a lot of nodding on that one because you could update this, read, update, and see the old version of this, update this. 4, 8. Yes? Okay? Not okay? A lot of unsures? Let's see. So is this okay? All right, so I'm going to read 4, write 5, write 6, write 6, write 7, write 7, write 8, write 8, read 8. Could happen on a local machine. 8, 9. Yeah. 9, 9. Not nodding. 9, 10. 9, 10. What? Still good? Okay. 10, 10. 11, 10. Yes. It can't. You're right. Whoa, sorry. Yeah, the second 9, 10 was wrong. All right, this can't happen. This is inconsistent. Right. Right, because once I've seen B equals 10, that means that A also must equal 10, at least. And so my next read of A needs to see at least 10. Now, so there's the inconsistency. It's subtle. If you just looked at either A or B, everything's fine. If I just look at A, it just monotonically increases. If I look at B, it monotonically increases. This is strongly coherent, but it's inconsistent. The inconsistency on the bottom. So there's no incoherence here, but it is inconsistent. Okay, so just to finish up the inconsistency, this is another classic example. Suppose I run a race, and each process tries to set a flag, and then if the other process has not yet set the flag, it can print out, yeah, I won, right? And so which of these can happen, which of these outputs are legal under a strongly consistent system or a strongly coherent system? Right, so you could, I think, easily imagine seeing any of these first three, right? That here A set the flag, before B got to set the flag and prints out its answer, which means that B is going to see the flag is set and not print anything out. The reverse could happen. Or both of them could set the flag, and then neither one could win the race. Right. The question is, could you ever see either of these? And if all we're looking at is coherence, right? If there's no guarantee across multiple locations, then this could happen, right? Because you could see, I can write one value and then read another value, and we know that those values have a relationship, but just looking at one location, I can't enforce that. But if I'm enforcing consistency, then this shouldn't happen, right? Because it constrains both reads and writes. So again, could this happen in NFS? Could you get down and have both sides think they won in NFS? Right? Yeah, you could. So it's not going to give you this type of strong consistency, even though we didn't think NFS was going to be incoherent. Right? You'd see these monotonically increasing numbers, but it wouldn't give you the consistency in this case. Okay. So with those definitions, now we can begin to talk about specific points in the design space. And so one popular place to start is sequential consistency. So this is Lamport's definition. There's a lot of words here. I'll pull out the key ones in a second. But the idea here is the result of any execution is the same as if all the read and write operations of all the processes were executed in some sequential order, and the operations of each individual processor appear in this sequence in the order specified by its program. Okay? So the things to pull out here are that there's a partial order defined by program order. So that's the individual process, the sequence specified by its program. And there's a total order across all these partial orders that you can merge these partial orders into a total order. Okay. So we've got the sequential order that can be made that's consistent with these partial orders. So let's give an example of this. So if you've got three processes that each, in this case, issue 4 operations, 1, 2, 3, and 4, each of them is issuing 4 operations. We need to, under sequential consistency, we need to be able to draw, some sort of line that is consistent with what they did and orders all these events. So if I could go through and say that, well, what really happened in the total order was this happened, then this, then this, then this, these, then if I can come up with an order that is both consistent with the local order, but also consistent with all the operations in a total order, then we've got sequential consistency. Now, it doesn't mean, of course, that they all actually implemented in that order. Right? They're allowed to have concurrency, but the only concurrency they're allowed to have is concurrency that doesn't violate these constraints. So as an example of this, suppose that I had a system where process 1 writes 1 to A, then it reads B and it sees that B is 2, then it reads A and says that A is 2, and then it writes a 2 to C. Right? And process 2 is going to go through and see that A is 1, write 1 to B, see that C is 2, write 3 to C. Here I see A is 1, write 2 to A, write 2 to B, and read 3 from C. Right? And the question is that sequentially consistent? Right? Is there some order of these events that can be globally ordered? So I could say, well, if I wrote a 1 to A and then I read 1 from A, okay, that makes sense. And can I walk that all the way through? And in this case, I can. One possibility is that I write A, read A is still 1, write B, see that A is still 1, make A 2, see that B is 2, and so on through the sequence. Right, so that's kind of the game that you have to show could be played if you want sequential consistency. But as I think you've discussed, sequential is pretty strong, but it's not perfect consistency. Here's a trivial example. Suppose that on one machine, I write A and then I write B. And then on another machine, I sleep for a year and I read A and then read B. Okay? So I go to one machine, I write some values, and then I sail across the country, I bring up another machine, and a year later I go and see what are A and B. So which of these is legal under sequential consistency? Right, is this legal? Sure. Right? I can do these two events, 1, 2, 3, 4. Right? That's a total order that's consistent with my local orders. Is this legal under sequential consistency? It is, right? I can go 1, 2, 3, 4. That's two partial orders that are consistent with a global. That's a global order that's consistent with those two partial orders. Not at all what I expect from this system, right? But it is legal under sequential consistency. What about just to complete the game? What about these two? Right? Could I read A as 1, B as 0? Yeah. Or A is 0, B is 1? Yeah, this is the same problem we saw a couple slides ago, right? So all these are legal under sequential consistency. Not at all what I would expect, right? So something is still not perfect memory. Right? And so the missing constraint is real time. Right, so go back to if we could look at the freshness dimension, there's a semantic called delta coherence. And delta coherence says the maximum real-time delay from when a write completes and a subsequent read begins, such that the read must return the value at least as new as that write, is delta coherence. And so NFS was roughly delta coherence with delta equals 30 seconds. And so one way to view linearizability is that it's sequential consistency plus delta coherence with delta equals 0. Right? That we have to sequence everything, but we have to. So here's my the definition, right? That I need to have all the read and write events appear to occur in some sequential order, consistent with program order. So that's all sequential consistency. But I have this additional constraint that it's not only consistent with program order, but also with the global real-time order in which the events occurred. Right? And so the kind of distinction in this memory model is that sequential consistency lets me reason about the ordering of reads and writes. And if all I know about, if I'm completely within the system, and the only way to communicate between processes or between threads is with reads and writes, then sequential consistency looks sensible. It looks, there's nothing, imperfect about it. But if there's any other channels of information outside of your system, like time, or a phone call, right? If I write some files and then call up my buddy across the country saying those files are written, right, there's this additional channel, and sequential consistency doesn't give you guarantees against that additional channel, but linearizability does. Right? So, linearizability does, give us some very strong guarantees. Assuming that I really do walk over to one machine, say write A, write B, the machine says, yep, those are done, and then a year later I do read A and read B on some other machine, which is legal under linearizability. Right? Just this. These can't happen, which is sort of what I would expect. Now, I should kind of close things with some other discussions of linearizability. That above definition has some redundant constraints. Right, I got to linearizability by starting off with sequential and then strengthening that. But you can get to linearizability in other ways as well. In particular, as soon as you say that all read and write events appear to occur in the global real-time order in which the events occur, you've got linearizability. Right? And this is because because of this composability property, that once you've got atomic loads and stores, atomic reads and writes on individual operations, that strong coherence, that very strong coherence property, turns out to be equivalent to this very strong consistency property. So there's sort of the singularity. When you get down to, in my three axes, once you've got kind of the strongest coherence, that actually turns out to be equivalent to the strongest consistency and also the strongest freshness guarantee. Okay. So is our problem solved? Right? We've got our definition of the right answer, linearizability. Right? That's equivalent to this very simple local memory. It provides you this ability to reason about atomic reads and writes. And even under that world, reasoning about distributed programs is going to be hard, but at least we've got that. Seems like weakening is going to be bad, so it seems like what we want. But there are two problems with that as our definition. The first is that there are fundamental limitations that we have to deal with in our distributed system. One of them that I'll talk about is CAP, consistency versus availability versus partition resilience. There's a trade-off here. That if I want this strong consistency property, I'm going to have to give up something in these other properties that I very much want. I like availability. I like fault tolerance. Right? So what am I going to do in those trade-offs? And then I should also point out that just this read and write API is limited. And so we may want more than that, and that's going to change what we want, perhaps from our memory model guarantees. So let me talk a little bit about the CAP theorem, and then maybe we could take a short break. The CAP theorem was popularized by Eric Brewer. I say popularized here because you can go back in the literature and find a number of people that observed this impossibility result, but they didn't manage to package it up as nice as Eric did. And so Eric gets credit on this front. So what the theorem says is that it's impossible for a system to guarantee sequential consistency, or by extension anything stronger like linearizability, always availability, and partition resilience. Right. Now I should say here that this has turned out to be the catchy answer, and it is a useful way to think about this problem, but it is a little bit weird in that we're looking at kind of two properties of the semantics of your system, or the way your system works, consistency and availability. That's something that you can design for, but partition resilience, this is a sort of a different dimension of how does your environment treat you, right? Can failures occur? And almost always when we're designing distributed systems, you sort of have to figure failures might occur. And so it to me is really that in a distributed system you've got to deal with either consistency or availability because failures might occur. But CAP pulls it out as a separate parameter. What it says is that if you want strong consistency and always availability, you can only do that if there's no partition resilience. That is to say, if you assume the system is 100% available. Right? The network never fails. You can have consistency and partition resilience only if you're willing to give up always availability. You may have to block requests if failures occur. You can have always availability and partition resilience, fault tolerance, only if you weaken consistency. Right? You've got to do one of these three things. Now, CAP is one of the famous fundamental limits. There are other limits. Lipton and Sandberg have a limit that basically on the performance front that says that if you have sequential consistency or stronger, then there exists at least some requests or some request pattern where the time for a read plus the time for a write must exceed the diameter of the network, the time to get across the network. And that kind of is for the obvious reason, right? That if you want that read to be able to observe that write, somehow the information needs to get across your network. So what this says is that if you want, if we agree from the previous discussion that linearizability or is what we want, we're going to have to give something up on one of these fronts. Now, one answer is, well, you just have a reliable network. And some people argue that in a data center we can do this, maybe. If I'm building a data center, I probably still want to think about the case where the network gets partitioned, and do I want to stop things at that point or let things get confused at that point? I sort of need to make a decision if that unexpected event occurs. But maybe you just design your system, assume that everything will be okay, and hope that you've got a new job before the data center goes down, right? That might be okay. But if we go to larger scale systems where the network is less controlled, I don't think there's any argument that assuming a perfect network makes sense. If I go to a mobile environment, or if I go to even the internet, I'm going to have to give up. I don't have partition resilience, or I don't have a perfect network. The network will sometimes be down, and so I'm going to either need to give up availability or use some, relax the consistency and use something like causal consistency. So, all right. So what do I mean by relaxing the consistency? Is there anything sensible we can do if we can't have strong consistency, we can't have a perfect network, but we need availability? Like, for example, if I'm on a plane and I want to look at, when's my plane going to land? I got my itinerary on my tablet. I want to be able to access that data then. How are we going to deal with that? And so causal consistency does allow highly available systems, even if the network is asynchronous or unreliable, which is my way of saying it may partition, or made appear to partition. And this gets used in things like a Dropbox, I don't know if it's used in Dropbox, but if you had a shared storage system like Dropbox where you want to be able to let people access data offline, you could have causal consistency. Coda has a variation of it, for example. Also, if you maybe had a multi-data center replicated storage system, right? You want disconnected access. Right? You want to be able to continue to operate even if my laptop is disconnected from Dropbox, or even if there's a disruption between data centers. And so in that world, we need always availability and partition resilience. We still want to be able to reason about consistency, and so causal does give us some ability to talk about the consistency in the system. So here's a traditional definition of causal. It's a little bit informal, and I'll make it more precise a little bit later. But we'll start with kind of the simpler intuition. So what causal consistency is traditionally defined to say is that memory operations that potentially are causally related are seen by every node in the system in the same order. Okay. It also goes on to say that concurrent writes may be seen in different orders on different machines. Okay, so that's a little bit obscure, I think, but it helps to see some examples. So under causal consistency, suppose that A and B are both initially 0, and process 1 writes a 1 to A, and then it writes a 1 to B, and then on process 2, we read a B. Okay. What does causal consistency say must happen when we read that A? Right, under causal, we've got to see the new version. Why is that? Because some program wrote A and then wrote B. And it's quite possible that that value A that it stored, the value B that it stored depends on A. And that one way to think of this is that maybe we know ahead of time that that program is only going to update B after it's updated A. There's something that I now know about that program's execution if I see B is updated. So if I see that B is updated, I know something about its execution, and so I know that A must have already been updated. So when I read A, I'd better see the new version. And you can kind of see I'll formalize this more later, but these arrows that I've shown you are kind of an important idea that if there's a path from, anytime I read a value, there'd better be a path from that value. And then once there's a path from that value, then any subsequent read had better see any writes that occurred earlier on that path. There's another example of this. Let's look at a 3-node example. So that showed that writes get ordered by causal. Here I'm going to show reads and writes getting ordered against each other. So suppose that I write A equals 1 on one machine, read A equals 1 on another machine, write B equals 1, read B equals 1 on a third machine, and then go and read A. Right? What do I have to read? And again, causal consistency requires me to see the updated value of A. And again, the reason, the sort of potential causal relationship, is that once P2 has seen A equals 1, and then writes B equals 1, this updated B may depend, kind of the way the program executed, on seeing this A. We don't know what happened in the program. We just know that it did this read and this write. Maybe this read helped cause that write. Maybe this write could never have occurred if this read hadn't occurred. And so if someone else sees this write, they'd better also be able to observe the read on which it might depend. Okay. So, yes?
How can we implement this causal consistency?
Yeah, so the question is, how can we implement this? And we'll go through implementation in a fair amount of detail. A naive implementation, right, is that any time you send information to another machine, you send it every single update you've ever seen, right? And if that occurred, then sort of, well, P2 now has every update from A, and so when it sends its updates to P3, not only does it send its updates, but it sends every update it's ever seen, right? And now P3 has seen everything that it might have depended on. But that's a very arm-wavy. We'll talk about implementing causal in the next section.
Have to be on different processes, different machines. These processes have to be on different machines.
Well, the semantic is independent of whether you're on one machine or many machines. The semantic, this can be implemented in a peer-to-peer way with direct communication between machines, or it can be implemented with a client-server architecture. Right? So the semantics is independent of the implementation strategy, and we'll see implementing it both in a centralized client-server way and also in a distributed, more of a peer-to-peer way. Okay, so this defines somewhat informally causal consistency. Gives you some intuition for that. Let's just see why, give an example of where causal is weaker than sequential. I think it's obvious that it is, but let's get a concrete example of it being weaker to get a feel for why it's weaker. Here's an example execution that is causally consistent but not sequentially consistent. So what I've got happening here is one process is incrementing a value and writing it to A. Another process is incrementing a value and writing it to B. And then we have two other processes, 3 and 4, that are reading A and reading B. Okay. And something that can happen under causal consistency, I believe, is process 3 could say 1, 1, 1, 2, 1, 3, 1, 4, 2, 5. As soon as this slide is over. Yes. Yep. Yes, we'll break after this slide, so hang in there. And then process 2 could see 1, 1, 2, 1, 3, 1, 4, 1, and 5, 3. So why is that okay under causal? Because these writes are what's called concurrent. That there's, if I see that A is 957, that tells me nothing about the current state of B. I don't know anything about where this program is in its execution. And so it's fine. If I see 957 and 13, that's fine. Right? That's a legal thing to happen here. So in this case, maybe process 3 has a fast connection to B, but a slow connection to A, and so it sees, B being incremented rapidly, but sees A being incremented more slowly. And that's a legal thing that could happen here. And similarly, process 4 might have a fast connection to A, but a slow connection to B. This is not sequentially consistent. Right? There's no way that I can order these events into a single order that makes sense. Right? That's consistent with A being monotonically increasing and B being monotonically increasing. And I think that's right. Just can't do it here. Right? That once I pick one, if I pick this one, I can do these two first, but then if I pick this one next, I can't ever put any of these into the order. So it is a definite weakening compared to sequential, but there's some hope to still be able to reason about the programs because of this sort of causal relationship. Right? It's a distributed system. Things happen in parallel, but at least I can capture the causal relationships. So let's pause now. When we come back, I'll finish talking about kind of the semantics of causal consistency, what some of its pitfalls are, and but also argue that it's the best we're going to be able to do, and so we'll have to live with those pitfalls. And then we can begin the discussion of how to implement some of these semantics. Okay, so let's take a 5-minute break, and we'll restart. Okay, so before we get started with new material, let's pause for a second and just take any questions or discussion about what I've covered so far. The first question was on this example, which is admittedly a little subtle, and that's why it's here. So what was the question? Yeah.
The question is that you said that it read 910 for the first time. That is okay because the connection to A might be slower. So can it not be the same case when it read it for the second time and it still got 910?
Right. So the question is, if this first read of 910 was legal, that was a legal state, right? And it could happen, quite sensibly could happen in a system, because of maybe the read from A is the connection to A is faster than the connection to B, or just maybe there was a scheduling event where this just didn't happen for a long time. Why then does this become illegal? If it was legal once, why isn't it legal again? And the answer, I think, is that when I read that B equals 10, that tells me something about the state of the system. Right? It tells me that this process has gotten at least this far, right? Which and set B to 10, which means that it has already set A to 10. I know that about the system. And so it's absolutely true that we could implement a system where you would see this. Right? You could see this in NFS. Right? I could, if I replace these, think of this as a write and a close, write and a close. In NFS, this could happen, where I would read, read 9.9 from my cache, let's say, and then read 9 again from my cache, but then have to do the timer goes off, I have to do a refresh, and I realize that the file has changed, and so I read the new version. But A is still within its window of 30 seconds, and so I continue to read from the cache, and I read my next value from the cache, let's say. This could happen in NFS. So it's absolutely the case that you can build systems where this would happen. But if you do that, you've lost the ability to infer from reading a value of B what happened to A, that this ordering must have occurred. And so that's exactly the trade-off in these designs, right? I can build NFS and allow this. It's simple and often right, but occasionally wrong. Or I can enforce sequential consistency, and then this would be illegal, but I'm going to have to go to more trouble in my implementation to make sure that this never happens. And I'll have to take steps to make sure this can never happen if I want sequential consistency.
So my question is, why is it illegal?
Why is it illegal? So again, it's illegal because once I see a 10, right, the next value that I read has to be consistent. So this gives me a global order, right, of events. Or sorry, it gives me a partial order over here. Right? And this partial order says these are the things that happened over here. There's also a partial order that says I increment this and then I increment this, which means that once I see that this value has been incremented, it's safe for me to assume that this value has been incremented. Right? And so there's no way to reconcile those two partial orders. Okay? Make sense? Okay, there were a couple of other good questions in the break, and I try to remember them. One question, I'm forgetting them. What were those great questions? So can you remind me of one of your questions? Yeah.
One was the difference between the sequential consistency and linearizability.
Okay.
And the other was on the last slide, that is how that is not how is it causally consistent?
Right. Okay. So the first question, was looking at trying to get a better intuition for the difference between sequential consistency and linearizability, right? And I've sort of said the difference is this additional constraint of time, right? That we're not going to allow staleness. But I illustrated that with a fairly absurd example that maybe didn't convey a whole lot of intuition, right? Because it is so absurd. Right? So let me give an example that is less absurd, perhaps. It's a system we built, so I think it's not too absurd. A few years ago, we did build a system that enforced sequential consistency, but did not enforce linearizability. And we did this actually to circumvent the cap limitation, because we also restricted the workload. So the system we built had was an information dissemination system. So think of a single web server where all of your updates occur. I think we were looking at a sports site, so the Olympics website, where updates are occurring at your main server, but the load is very high and you want good latency, and so you have a bunch of satellite servers that people are reading from. So in our system, all the updates occurred in sequence at this centralized location. All the updates were sent in FIFO order from this centralized location to any one of the distributed locations. If a client reads from any one of those distributed locations, they're going to see the updates progress in sequential order. And so if I look at all the reads and writes in the system, I can create a global order, a total order, that's consistent with all the partial orders of all the reads that everyone did and all the writes that happened in that central location. But in our system, if a failure occurred, maybe one of those satellite locations doesn't get updated for 30 seconds or a minute or 5 minutes. Clients can still read from it. They're still seeing a sequentially consistent moment in time. But they're not seeing the value that they would get if they went to the central location. Right? And so later on, when the network connection comes back, those updates will get pushed down in FIFO order, and they'll continue to see a sequentially consistent view of the system. Right, so in that example, everyone sees updates that are consistent with the sequential order, and everyone sees sequential consistency. Right? But some of my clients are seeing stale data, maybe because their server's fallen behind, it's just overloaded, or maybe because there's a disruption and it's not seeing all the updates. Okay. So that's an example where it's sequentially consistent, right? And it kind of makes sense to users, but it's not linearizable because sometimes the values I'm seeing are not the current values. One way to think about this is if you've got these partial orders, the reads at a disconnected server kind of get crunched up as if they happened at this moment in time right before the disconnection. So if I can distort time that way, it still looks sequential. But of course, I'm not allowed to distort time under linearizability. So that's one other example that maybe shows the distinction between sequential consistency and linearizability in a more useful example. Okay, then the other question was looking at the example on causal. I think there was a good point to be made there. So, so again, the question here was, kind of understanding why is this a legal causal thing to do? What's the relationship between these values? And so again, the point here is that these two processes are completely independent. So if I tell you that A is 37, that tells you nothing about B. Okay. But causal does allow me to bind these things together in a program. So for example, if process 3 were now to write to location C, the string, I just read that A was 2 and B was 5. All right, so that's the contents of C now. And some other process reads C and sees that someone else reports that they just read a 2 and a 5. Right. They're now entitled to believe that if they were to read A, they would see at least 2. And if they were to read B, they would see at least 5. Right? And it would be weird if that wasn't true. Right? If someone told you, I just read a 2 and a 5, and you saw a 1 and a 4, you would know something's not quite right. That would be a violation of causal consistency. So as things currently stand, nothing binds these together. But if I now have an event that depends on something I read, then anyone that sees my event is guaranteed to read things at least as fresh as what I saw. So are there any other questions or discussions? Yeah.
But if the process P4 writes to a memory location D, and the process P5 reads from this particular location, then it will get the value of A and B, 5 and 3. Previously it was getting 2 and 5.
Yeah.
So won't there be some...
Okay, so yeah, so if process 4 were at this moment to write a 3 back to B. All right, so it just sees 3, it writes 3. Okay. And anyone reads that 3. Let's say it writes 3.1. Right? So it writes 3.1 to B. And some other node reads 3.1. Right? If they were then to read A, they would see at least 5 under causal consistency. Because, if I change this program to say, well, one, print these things, but if B is at least 3, write, or if A is at least 5, write B plus 0.1, some program like that, then when I see the 3.1, I know that the 5 must be there. So that would bind them together. Any questions or discussion on this? Okay, so, yeah. There is. Linearizability, so the question is there a relationship between linearizability and causal consistency? And there is. The relationship is that linearizability is strictly stronger than causal consistency. That any execution that is linearizable is also legal under causal. But it's stronger than, so not all causal executions are legal under linearizability. Yeah, so there is we'll actually talk in a minute about, there is a way to order different semantics, stronger than versus weaker than. I'll define that in a minute, but for the semantics we've talked about, Linearizability is strictly stronger than sequential. Sequential is strictly stronger than causal. Causal is strictly stronger than FIFO. I'll show you in a minute. So there are a definite ordering among these, but not all semantics are orderable. There are incomparable semantics that you can come up with. But these are kind of the natural, these feel very natural, this sequence.
For example, 2 pi and 5 3, are they comparable or not? P3 is reading 2 pi and P4 is reading 5 3.
Yeah.
So are they comparable or not?
They're legal under causal. They're illegal under sequential. They're illegal under linearizability.
So then you said that some, results are, they are not comparable. Semantics.
Oh, semantics. Right. So the particular values being read are for this execution, we can ask: is this execution legal under causal? Yes. Is this execution legal under sequential? No. Okay. There's a separate question of the semantics, of comparing the semantics themselves. Right. We can say is causal weaker than sequential, or sequential stronger than causal? And we can say yes. And that is a definition that talks about the universe of all executions that are allowed under causal is bigger and includes the universe of executions that's allowed under sequential. All right, other questions? Okay. So causal has, some pleasing properties, we could, maybe it's plausible that we can reason about systems that are causal, but that's kind of the good news side of things. I want to talk about the bad news for causal. Here's the big problem that you run into, and that's concurrent writes. Suppose that instead of updating A and B, we have two processes that are both updating A. To make it more personal, suppose that you and a collaborator are both updating, some file, some source code file, or maybe a presentation you're trying to give, a document you're editing, and so you can have two different nodes in the system update the same file, same memory location. And what should happen if someone reads from that location? So the traditional definition of causal that I gave you handles this case, includes this case. It says that, those were two independent reads. Your writes, you legally would be allowed to see 2 and then later see a 1. You're legally allowed to see a 1 and then later see a 2. Or you're legally allowed to see a 2 and never see the 1. Or vice versa. Those are all legal things under causal. But it's not okay for a system to throw away my edits because I was editing the file at the same time you were. Because I don't think that's okay. You'd be upset if you were editing a Word file or a document and you added an entire section of prose. And someone you were working with fixed a spelling error, right, on one of the words. And then you come back the next day and all your updates are gone, but that spelling error is fixed. You'd be very mad at your partner, but in fact, you shouldn't be mad at your partner because the system was just implementing causal consistency and it's not their fault. They never saw your updates. That's a legal thing that could happen under causal consistency. And so we usually don't think that's okay. And so this comes up in all these systems that give you disconnected access. They have to worry about what are called write-write conflicts, where there are two concurrent updates to the same object. Again, using my Dropbox example, on one machine I might edit my travel itinerary. On another machine I might make a different edit. I want both those edits to survive somehow. And I'm going to be upset if the system throws one of them away. And so, what do we do when multiple updates go to the same object in parallel, concurrent updates? So, we could keep one. We could ask the user. So we could keep one. Right? We could throw away the other, just keep one. I've argued that that's probably not acceptable in a lot of contexts. we could ask the user, we could pop up a dialog box saying, there's 2 versions of this file, what do you want to do? We could automatically merge the 2. Right? And all of these things get done. It really depends on the application. So I'm going to presume that most of you have used version control systems, where you and collaborators can check out files, edit them, and check them back in. And what typically happens in these systems is that if 2 users edit the same file, sometimes the system will realize that you edited this part of the file, the other user edited this part of the file, and it will just merge those updates. But other times it will say that you're kind of trying to edit the same thing, and it doesn't know what to do. And so it'll typically show you both edits and let you manually fix the problem. And this happens in different systems. In Coda, for example, if you had 2 different users, well disconnected, create new files with different names in the same directory, Coda says, yeah, I can handle that. Just keep both files. But if you have 2 users edit the same file that's not a directory, Coda gets confused and it'll punt and let the users figure out what to do. So I'm going to redefine causal consistency here. And I'm going to require that instead of showing you one of those 2 answers when there's these concurrent updates, what the system should do if it learns about concurrent updates is give you both answers. Right? That if consistency's job is to order events, remember my definition of consistency said it decides on the ordering or restricts the ordering of different events in the system. Well then, rather than have my consistency layer try to say that either 1 happened before 2 or declare that 2 happened before 1, neither of those things is true. What really is true is that both these updates happen concurrently. And so the state of the system at this point should be that the value of A is 1 and 2, that these 2 updates are both the current value of A. Right? Now, so I'm going to redefine causal consistency to say that you need to return the set of most recent writes to an object rather than the most recent write in this causal order. So if there's multiple writes, you may return multiple values. But then that's not what applications necessarily expect. And so to deal with conflicts, you'll want an additional layer above the consistency layer to resolve these conflicts. And as I've said, different applications or different systems will resolve these conflicts in different ways. Right? And so causal consistency will give you this as raw material, and then that's well defined, and then some conflict resolution layer, which may be application specific, will hand maybe a munged value up to the application. So you could, for example, filter the results to resolve the conflict. Maybe you're in a system where we don't care if we lose an update, and so we can just have my conflict resolution layer just pick one of those answers. Systems have done this. Oracle had, I think, a library of 13 different conflict resolution decisions that you could just pick one of the 13. And sometimes you'll pick the highest value. Sometimes you'll pick the lowest value. Sometimes you'll pick the value that had the highest real-time update. Sometimes you'll pick the value that came from a preferred primary site over a concurrent update at a different site. So you can do all these things. So my conflict resolution layer maybe picks one of those 2 values, or maybe it merges them. Maybe what this thing is an accumulator, and so it's going to add those 2 values together. Or maybe there's some semantic that I don't understand, but the conflict resolution layer does, and it just picks 97. Or it picks some other value. Right? That's going to happen in this conflict resolution layer. And that's very application specific. So that gives us a different definition, or a tighter definition of causal. All right, so we're going to say that an execution, you run a program, it does a bunch of reads and writes. We just look at those reads and writes. That execution is causally consistent if there exists a directed acyclic graph, call that G. What's in that graph? It contains a read or write vertex for each read and write operation in the execution. Okay, so you take your execution, take all the read and write events, and each of those things becomes a vertex in this graph we're creating. Okay, we want a graph, so we need some edges too. Right, so for these edges, we're going to add edges among these vertices that impose a partial order. In this graph, we'll call it proceeding in the graph. So proceed in G. So in this graph, they proceed on these vertices such that G satisfies the following checks. Okay, so far what we've said is take all the reads and writes. Each of those becomes a vertex. And there better be a way to add edges, directed edges, among these vertices to create a graph that meets these following checks. Okay. The first causal consistency 1 requirement is sequential ordering at each node. Okay. What this says is that the serial ordering of operations is reflected at each node in G. All this means is that if you look at the vertices that represent a given node's reads and writes, you need to draw an arrow from operation I to operation I plus 1. Okay, so we're just adding a sequence of operations at each node. Okay? So we need those edges had better be there if you're going to be causally consistent, which just means there's a partial order in our system that's going to reflect the operations at each node. The second requirement is that a read returns the latest preceding concurrent writes. So for any vertex R that's a read operation, read O, our result contains all the writes W of O that precede R and G and that have not been overwritten by another write of O that follows W and precedes R. So this is a complicated equation to express all that. But again, what I'm saying here is that if I look at a read operation, there had better be a path. It's going to so that read operation returns some result, some list of writes, usually one thing, sometimes multiple things. For any one of those results that were returned, there had better be a path from the write that produced that result to that read. And there'd better not be anything on that path that's another write to the same object, right, that obliterated that earlier version. Okay. So if I can create a graph where all the operations on a node happen in order, and anytime I do a read, there's some earlier event that I can look back to in the graph that produced those results without being overwritten by something else, then I've got causal consistency. Okay. Is that questions about that? Yeah. So if it's not connected, right? So it could be not connected if there's a node whose reads are not affected by some other node's writes, and whose writes are never observed by another node's reads, and that's fine. That's still causally consistent, right? So it turns out, right, it's causally consistent. If you go back to my example, actually if we look at my example, my classic example, my standard example here, if I get rid of P3 and P4, let's forget about those for a second, and look at, A does a bunch of writes and B does a bunch of writes, that's causally consistent. That's fine, right? There's no dependency between the two, and so it's legal under causal consistency. Okay. So let's see, with this graph-based definition, let's walk through my example and see what's going on. So step 1, I told you, was to create a vertex for each read or write operation by a node. All right, so my graph has to include a vertex for each read and write operation by a node. And so here's process 1. It's writing A equals 1, 2, 3, 4, 5. Process 2 is writing 1, 2, B equals 1, 2, 3, 4, 5. And then I gave them in a funny order to make the arrows look nicer in a second. Process 4 is going to read 1, 1, 2, 1, 3, 1. I'm skipping the 4, 1. I hope that's okay. And the 5, 3 that didn't fit. It doesn't change the shape of the graph very much. And similarly for process 3, reading 1, 1, 1, 2, 1, 3, 1, 4, which I'll skip, and 2, 5. So step 1, I need a vertex for each read and write operation. Step 2, I need for this to be causal, I need to be able to create a vertex, an edge from operation I to operation I plus 1 at each node. Easy to do. And I need to be able to create an edge so that when I do a read and I see A is 1, there'd better be a way that this A equals 1 is only a legal result if there's a path from that write to this read in which this is the latest write to that value, to A. Okay, so I add an arrow here. Since I see 2 is 1, A equals 2, I'd better add an arrow here. I add an arrow here. I skip my 4, but I'd add an arrow here to see that A is 5. Right, so that accounts for my reading of A and makes that legal under causal. I do a similar thing down here for reading B, and then I also need to be able to show that it's legal for me to be reading these values of B. Okay, so if I want to be able to read B equals 1, there'd better be a path where from the update of B equals 1, and so on through the system. I forgot to add that path, so pretend in the next slide that there's a path. So I forgot this path and this path. Okay. I should have pretended that was a test for you, but it was an error. Okay. I also require there to be, to account for what was observed here. Here I read, so this reads B equals 1, but I didn't need to add any additional arrows other than the one I forgot to add, right? Because I can follow the path back and see B equals 1 and not see any additional updates to B. That's a legal thing to read here under causal. But when I read the 3, I need there to be a path back here. Right, so I add that path. And that's a legal thing to read under causal. Similarly, to read this 2, I need there to be a path back here. Okay. So now I've added all my edges, except for the 2 I forgot, sorry. And now I can ask, is this causal? And it is, because I run my checks on this system. Is there an edge from every operation I to I plus 1 on every node? Yes. Is there a path from, for every read, is that read returning the latest writes to that object given these edges? Yes. Right. So this is legal under causal. Okay, so that's sort of a more a graph-based way to think about causal. Yeah.
The latest write, I mean, if you see in 5.3 and 2.5, I mean, after B was updated it to be 3, I mean, it was again updated to be 4 and 5.
Right.
So need not be considered the latest value of 4 and 5 and say that it is not causal.
Right. So here the question is, we in this graph we know that after B was 3, it became 4 and 5. How is this how is 3 the latest update? And it's latest in the sense of a test on this DAG. Right. That if I look at this directed acyclic graph and I look at this read, I can follow back these paths and look for writes of B, and the latest write of B that's not updated by any other write of B on this kind of reverse tree through the system is this one. And there's no other write of B on the envelope walking backwards on this reverse tree that's either newer than this or concurrent with this. And so just looking at the graph, right? Forget about the real world, forget about real time. If I just gave you this graph and you run this test, then this is the latest write from this node's point of view. So one way to think about it is reverse the arrows and look at the tree that grows backwards out of this node, right? And following all those paths down the tree, there's some, whenever you hit a write to B, you keep it and you can stop going down that path because you don't care about any writes to B that are reachable there. Okay, what writes to B can you reach by going down the tree that way? Okay. Any other questions? Okay, so the way that I'm going to wrap up today is to argue that causal is a satisfying place to be, despite these challenges that it poses from things like right-right conflicts. And the reason that, well, whether you're satisfied with it or not, you're stuck with it. Right? And the reason you're stuck with it is there's nothing stronger that you can implement. Okay, so here might be a theorem you might propose. And you might propose this theorem by looking at the last 30 years of work in this area. That's probably too aggressive. 91. So we're just 20 years. 20 years of looking at this area and looking at distributed file systems and observing that no one is, when people build distributed file systems that do disconnected operation, people build causal systems, but they don't really build anything stronger. In 20 years, they built some things that are weaker, but again, never stronger. So you might speculate that no consistency stronger than causal can be implemented in an always available system. We're trying to get the sort of other side of the CAP theorem. So CAP says we can't have sequential, says we can't have linearizability. We know from, trust me at this point, that there are systems that have been built that implement causal. We'll talk about how to build them on Friday. But there's a bunch of them out there. And so you might speculate that's the best you can do. So we can't have sequential. We can't have causal. Is there anything between there that we can have? And you might speculate the answer is no. That no consistency stronger than causal can be implemented in an always available system. So what do I mean by stronger then? We've talked about this a little bit already. Consistency semantic C1 is stronger than C2 if C2 admits all executions admitted by C1 but not vice versa. So if you look at every possible execution, the universe of executions, what we're saying here is that C2 is a bigger set, and it includes all the executions of C1 plus some additional executions that aren't legal. We saw that, for example, causal, so sequential is stronger than causal because anything that's sequential is causal, but not everything that's causal is sequential. A system is always available if and only if all reads and writes complete in bounded time regardless of what messages are lost. Okay. The key thing here is that I've slipped a partition resilience in here, right? That if there's a partition, you still have to be able to complete all your reads and writes. Okay. So is causal the best we can do? Turns out that conjecture is false. I can define systems that are always available and that are stronger than causal. One example is my no communication system. We talked about it just a minute ago. My disconnect system where it's not a connected graph. Reads of O, in this system, a read of O, of object O, always returns the most recent local write to O. That's legal under causal, right? Doesn't violate any of our constraints. Also seems kind of useless as a distributed file system, but it's legal. Here's even more useless. We can implement a system called only receive a sequence number as prime. All right, so keep a sequence number for every local read or write operation, and we're going to require all the requirements of causal, plus we're going to require that unless there's been a prime event, then none of your local state should have changed unless you changed it. We can define that as a semantic. I don't know this is a great definition, but that's you can define that. That would be strictly stronger than causal, right? It's causal plus some additional constraints. So my conjecture was wrong. On the other hand, these seem like really lame examples, right? These kind of are weird. So, okay, is there a meaningful way in which causal is the strongest? And there the answer is yes. But we have to bring in some new requirement that eliminates these useless systems. And so we have this intuition that these are useless. But why are they useless? Because they're not providing convergence. So convergence, I would argue, is an additional property that you want from a distributed file system. And that just looking at consistency, availability, and partition resilience doesn't capture all the things you want from a system, and all the things you need to understand when you talk about these trade-offs. So the intuition for convergence is that if one node issues some writes, other nodes ought to see those writes. And a system that constrains or limits when you can see those writes is less convergent than one that gets you those writes quickly. And so a system that never shows you the writes of another node is not very convergent. A system that only shows you the writes of another node if you've executed a prime numbered event, it's kind of convergent, but not as convergent as a system that might show you those updates whenever you can communicate. So when we look at those artificial examples, we can actually, in a principled way, talk about why they feel artificial. They feel artificial because they don't provide strong convergence, because they weaken convergence in weird ways. So when we talk about convergence, there is a range of convergence properties, right? The first system was completely unconvergent. The second system was weirdly convergent. What are some meaningful ways to talk about convergence? One is to talk about eventual consistency, which is a very annoying property because it's not really a consistency property the way it's sometimes defined. It gets defined in different ways. There are some definitions that I like better than this one, but this is a very commonly used definition. It's a very weak definition of convergence. If all nodes stop issuing updates and can communicate with one another, then eventually any object O, for any object O, a read of O would return the same result at any node. So if the system becomes quiescent and you wait a while, then eventually you'll be able to read the same result at all nodes. This is a definition pretty commonly used. I hate it, but it's a commonly used one. I hate it because it's not really a consistency semantic. It's not a safety property. It's a liveness property. It's weird. But it's very weak because it requires things like everyone stop issuing new reads and writes, and it requires things like everyone be able to talk to each other. And so, if a node crashes, this doesn't tell me anything about what's going to happen. If a network connection goes down, this doesn't require anything to happen. If a node keeps updating things, it doesn't require anything to happen. It's not a very strong property. At the opposite extreme, and there are gradients between these things, but the opposite extreme, we can talk about one-way convergence. This is a very strong property. What it says is that if node 1 can receive from node N2, then after some finite amount of time, N1 state should reflect all the updates that N2 knows about. Or if I can receive from you, eventually I ought to know what you know. And this is a kind of sensible property. Bayou kind of works like this, where I'll ship you some updates, and they'll reflect your state. So this is a property that kind of is, oh yeah, if a system gave me that, I'd be happy. Almost done here. We're right at my limit here. So here's what I can tell you, and this I represent to you as a theorem. No consistency stronger than natural causal can be implemented in an always available one-way convergent system. All right, so we've seen always available. Reads and writes can always complete, even if you disconnect nodes from the network. One-way convergent I just defined, said that if you can receive from me, then eventually you'll know everything I know. Actually, not just eventually, but after some finite amount of time. And what I haven't defined, I kind of did a little bit of wiggling on you. I changed causal into natural causal, right, which should make you a little suspicious. Turns out we have to add one more constraint for this to be true. So here's my definition of natural causal. Fortunately, none of this changed. This is all causal. We just add one additional constraint. And the constraint is that time doesn't travel backward. Okay? For any pair of operations, if U ends before V begins, then in your DAG, we don't want V to come before U. They can be concurrent, but you don't want the later event to happen before the earlier event. Right? And it turns out you do need this constraint to make the theorem go through. What's interesting is we had to bring in a little bit of information about staleness and freshness to make this work. But the good news is, although this is not commonly included in definitions of causal, this really is a new restriction. You can come up with executions that are causal, but not naturally causal. So naturally causal is strictly stronger than causal. But almost any sensible system you're going to build, I don't know of any system that isn't natural causal. So although it's a new formulation, it's just making explicit what we've always been doing anyhow. Okay. Now, I'm representing to you that this is a proof, but I'm not going to try to prove it in the negative 3 minutes that I have remaining. And this, I won't even represent this as a proof sketch. It's kind of the intuition for what's going on in the proof. If there's some implementation that claims to be stronger than causal, always available, and always convergent, those properties allow me to force it through an execution for any causal. This is probably too fast to do, but trust me, this is a proof. Maybe we'll talk about this a little bit on Friday if you're interested. Let me instead stop here and probably can answer 1 or 2 questions, but then we should have our break. Yeah.
How is this different from linearizability? Because you said time can't go backward, and linearizability is also mentioned that operations should take place in real time.
Right. So the question is, how is it different than linearizability? What it allows is to, even if 2 events happen in real-time order, it allows causal to treat them as concurrent. Okay? It just doesn't allow causal to reverse them. So causal is allowed to put them in real-time order. Causal is also allowed to make them concurrent, but causal is not allowed to put them in reverse real-time order in the DAG. No, in linearizability, if event V happens before event U in real time, event U completes before event V begins, then linearizability demands that event V happen before event U. It doesn't allow them to be concurrent. All right. Yes. Yes. Yep. Topological sort on the DAG. Absolutely. Okay. So thank you very much. On Friday, we may just say a few more words about semantics, but what we'll really talk about on Friday is building systems. We'll talk about building systems that enforce causal. We'll first talk about building systems that enforce linearizability and sequential. We'll talk about building systems that enforce causal. And we'll talk about what happens when we go from client-server systems to systems that allow more general communication or cluster systems that scale to much larger numbers of nodes. Okay, yeah?
So can we actually build a system which is natural causal and one-way convergent?
A system that's natural causal and?
One-way convergent.
Yes. Yeah, so we can build a system. So the claim was that, yes, we can build, this is a theorem, we can build a system that is natural causal. I guess, oh, sorry, this is the reverse. You're right. Thank you. Good question. There's nothing stronger, and we can, in fact, implement natural causal. And in fact, most systems that claim to just implement causal actually implement natural causal. So yes, it's tight. It is tight. We can build natural causal, and we can build nothing stronger under these constraints. Thank you. Good question. All right, so thanks, and I'll talk more on Friday.